Imagine this. Traveller, in the quiet dark of our solar system, 7 ancient wanderers are gliding inward at the very same moment as if answering a call only they can hear. You did not arrive here by accident. Something in the universe wanted you to notice this convergence. What are the odds that in the same narrow window of time, 3I Atlas, the largest interstellar object ever detected, drifts past the edge of Mars like a silent messenger from another star, a swarm behind it, a mystery ahead of us, and a question lingering in the dark? What if this timing isn't coincidence at all? Let's drift a little deeper. In most years, the inner solar system hosts no more than one notable comet, and frequently none at all. Comets are typically faint, solitary, and slow to approach the Sun. Their arrivals follow no special rhythm, each one a lone messenger from the outer reservoirs of frozen material that surround our system. Yet the year 2025 presents an anomaly that has drawn the close attention of astronomers worldwide. 7 distinct comets, Pan-STARRS, Swan Stereo, Atlas K1, Atlas G3, Lemon and Neat, are all approaching the Sun within the same narrow observational window. Their timing is unusual, not because such objects are rare, but because their arrivals have clustered with a statistical density that challenges expectations based on long-term comet observations. In isolation, each comet follows a familiar dynamical path shaped by gravitational perturbations over millions of years. These orbits originate in distant reservoirs such as the Oort cloud or the Kuiper belt, and their eventual inward migration is usually triggered by small gravitational disturbances, passing stars, galactic tides, or long-range interactions with giant planets. None of these mechanisms on their own predict a simultaneous inward migration of 7 unrelated bodies, and yet here they are arriving together, not by shared origin or mutual influence, but by coincidence that appears unusually pronounced. What makes this clustering especially compelling is that it coincides with the passage of 3I Atlas, the 3rd confirmed interstellar object ever detected in the solar system. Unlike the 7 comets which were formed from primordial solar system material, 3I Atlas originated beyond the Sun's gravitational domain. Its trajectory is hyperbolic, ensuring that it will not return. Its composition likely reflects chemical environments markedly different from those that shaped the comets born in our local nebula. From a scientific standpoint, the timing raises legitimate questions. Is the concurrence simply a rare coincidence, or does it suggest a deeper dynamical relationship affecting both interstellar and solar system objects? Statistically, the probability of such overlap is low, but not impossible. In large datasets, whether of comets, earthquakes, or cosmic rays clustered events occasionally occur naturally even without causal links. The human mind is exceptionally sensitive to patterns, and it is precisely this sensitivity that encourages both scientists and casual observers to wonder whether the sky is signalling something meaningful. The scientific challenge is to evaluate the pattern without overinterpreting it. Current data indicate that the 7 comets follow independent evolutionary histories. Their long-period orbits were set into motion long before 3I Atlas entered our observational reach. No gravitational interactions between them are possible. The distances involved are vast and their velocities differ by orders of magnitude. Similarly, electromagnetic forces cannot coordinate such large-scale orbital behaviour. Comet nuclei are far too massive for solar magnetic fields to significantly alter their trajectories. Thus, from the standpoint of physics, no mechanism presently known can herd these comets together, or tie their timing to an interstellar object. Yet the convergence remains striking in its visual and statistical form. Sometimes the universe generates patterns that carry no intention but nevertheless attract human attention. Rare alignments once observed naturally inspire further study not because they must indicate a hidden force, but because they represent opportunities to refine our understanding of the system as a whole. 3I Atlas itself remains an object of high scientific interest. As it traverses the inner solar system, it provides a unique chance to study materials forged around a different star. Spectroscopy has already revealed chemical signatures unlike those of typical long-period comets. It's brightening its early development of a coma at large distances and its non-repeating trajectory make it a compelling laboratory for interstellar chemistry and thermal physics. When interpreted together, the 7-comet swarm and the interstellar visitor form a tableau that is scientifically intriguing but not yet indicative of coordination or causation. Their shared timing invites curiosity, not conclusion. The responsible scientific stance is to observe carefully, analyse rigorously, and accept that nature occasionally produces timing patterns that feel intentional even when they are not. Yet there is value in these moments. They remind us that the solar system is not static but dynamic, a space of constant movement, long-term cycles, and occasionally surprising convergences. The year 2025 offers astronomers an unprecedented opportunity to study multiple comets under similar solar conditions. It also offers the public a chance to witness a rare concentration of celestial phenomena, inviting renewed engagement with the broader cosmic environment that sustains our existence. In the end, the clustering of 7 comets and the passage of through our atlas may reveal nothing more than the universe's capacity to surprise us. But that in itself is scientifically meaningful. Astronomical discovery often begins with anomalies patterns that stand out against a backdrop of expected behaviour. Whether or not this moment represents a deeper connection, it serves as a reminder that our solar system continues to evolve within a larger galactic context, influenced by forces both familiar and unknown. And in that sense, these converging visitors, local and interstellar, invite us to look upward, with renewed curiosity, recognizing that even in a sky governed by natural laws, mystery remains an essential part of scientific exploration. When evaluating the unusual clustering of cometary arrivals in 2025, astronomers must separate the visual impression of coordination from the physical processes that govern comet dynamics. 7 comets arriving within the same observing season create an unmistakable sense of pattern, yet the scientific method requires asking a more fundamental question. What would coordination look like if it were real? And more importantly, what does the actual data show comets do not simply fall toward the Sun? They follow orbits shaped by long histories of gravitational perturbations. Each object in the swarm, Pan-STARRS Swan Stereo, Atlas, K1, Atlas, G3. Limon and Neat began its inward journey thousands or millions of years ago, long before humanity existed to witness their convergence. The forces that initiated their motions are well understood. Passing stars that slightly distort the Oort cloud, the slow tidal influence of the Milky Way, and interactions with the giant planets. These influences operate on vast timescales, far beyond any mechanism that could link the comet's present-day arrivals in a coordinated manner. Yet the 7 objects do not simply arrive close together in time, they also display diverse discovery circumstances. Some, like Swan, reveal themselves first in hydrogen emissions detected by spacecraft, designed to study solar wind rather than comets. Others, like Stereo, appear as incidental captures and cameras pointed at the Sun. Pan-STARRS. Lemon and the Atlas discoveries arise from powerful sky survey telescopes scanning wide fields with high cadence. Neat, the oldest of the group in terms of observation history, has been tracked for more than a decade. The diversity of detection methods underscores that this swarm is not a coordinated assemblage, but a convergence recognized only because our monitoring capabilities are unusually broad and sophisticated. The emergence of modern wide-field surveys such as Pan-STARRS, Atlas and Catalina has dramatically increased our ability to find comets. These systems continuously scan the sky with automated algorithms sensitive to small changes in brightness and motion. It is therefore unsurprising that more comets are detected overall. However, detection alone cannot explain their synchronized perihelion passages. Surveys detect objects that are already inbound. They do not alter their timing. Their role is observational, not causal. Thus, scientists turn to orbital mathematics for clarity. When plotting the orbital elements of each comet, their inclinations, semi-major axes, eccentricities, and long-term source regions, nothing suggests common origin. The 7 bodies occupy different dynamical families. Their source reservoirs differ. Their orbital inclinations diverge significantly. These facts collectively argue against any shepherding mechanism, either gravitational or electromagnetic. Gravitational coordination would require a massive perturber, capable of influencing cometary orbits across tens of thousands of astronomical units a scale at which only hypothetical objects such as Planet 9 or passing stellar bodies could operate. But no such influence is visible in the orbital signatures of the swarm. The perturbations that shape these comets' paths arise from well-understood interactions, and none suggest a recent or shared gravitational event. Electromagnetic coordination meanwhile violates basic physical constraints. Solar magnetic fields affect charged particles in comet tails, not the trajectories of kilometre scale, nuclei composed primarily of frozen volatiles. Radiation pressure can influence fine dust grains, but not large bodies with substantial mass. Magnetic shepherding on the scale required for coordination is physically impossible within the electromagnetic environment of the solar system. The overarching conclusion, therefore, is that the 7-comet swarm represents coincidence rather than coordination. But coincidence of such magnitude remains scientifically interesting. It invites inquiry into long-term patterns in comet arrival distributions, the structure of the Oort cloud, and the influence of galactic tides. Periodic surges in comet activity may reflect the dynamic nature of the solar system's distant reservoirs regions, largely invisible to direct observation. Yet even as the 7 comets trace independent histories, the presence of 3I Atlas introduces a second layer of intrigue. Interstellar objects are rare. Prior to Atlas, only 2 had been confirmed, Oumuamua and 2I Borisov. Their arrival suggests that interstellar debris passes through the solar system more often than previously assumed, but still rarely enough that the timing of 3I Atlas alongside a 7-comet swarm feels conspicuous. From a scientific perspective, it is essential to avoid anthropomorphizing these alignments. The universe does not arrange events for human benefit, nor does it encode messages in cometary timing. But the cognitive bias toward pattern recognition remains powerful. Human intuition is tuned to notice clusters, to see meaning in proximity. This instinct once helped early humans detect predators or environmental changes. Today it colours our perception of celestial phenomena. To counter this bias, astronomers employ statistical tools, Monte Carlo simulations, Poisson distributions, and clustering analyses. When applied to long-term comet records, these methods show that apparent clusters do occur naturally. Random processes produce patterns that look intentional. The 2025 swarm is rare but not unprecedented on geological scales. Still, rarity alone grants scientific value. A year with multiple bright comets is an opportunity to compare chromodynamics, tail, morphology, nucleus, composition, and solar interaction processes under similar conditions. It allows researchers to observe how different bodies respond to the same solar wind environment as the Sun approaches a cycle of heightened activity. These comparisons can refine models of sublimation jet formation and thermal stress. Furthermore, the presence of an interstellar comet within the same time frame provides a unique cross-reference, a chance to contrast the behaviour of a foreign object with that of bodies shaped entirely within the Sun's gravitational domain. Differences in chemical composition, outgassing behaviour, and dust production between 3I Atlas and local comets may reveal insights into the formation environments of other stellar systems. Seen through this scientific lens, the year 2025 becomes not a coordinated event but an unusually rich natural laboratory. The sky's convergence is not a message but a data set. And yet scientifically grounded as this interpretation may be, the convergence still speaks in a quieter way, a reminder that our solar system is alive with motion complexity and the occasional coincidental beauty that prompts deeper reflection. To understand why the 2025 convergence feels so unusual, it is necessary to step back and examine the object at the centre of the discussion. 3I Atlas, the interstellar traveller whose presence has amplified public fascination with the 7-comet swarm. Whereas the swarm represents a natural concentration of solar system-borne objects, 3I Atlas belongs to a category fundamentally different in origin, chemistry, and trajectory. Its arrival offers an opportunity not merely to observe a rare visitor, but to scrutinise assumptions about how objects migrate through the interstellar medium and how frequently they intersect with planetary systems like our own. Interstellar objects are formed in environments profoundly different from those that shape the Sun's family of planets and comets. Their ejection may result from gravitational interactions within their natal systems, close encounters with giant planets, three-body instabilities, or early dynamical clearing as stars carve paths through their local galactic neighbourhoods. Once ejected, these objects become unbound, drifting through the galaxy on trajectories governed solely by the gravitational influence of the Milky Way. They do not orbit any star. Instead, they move as solitary debris carrying the chemical and mineral signatures of their parent system. For decades, astronomers expected such objects to be exceedingly rare in the solar system. Before 2017, no confirmed interstellar object had been observed, yet within less than a decade, 3 have now been documented: 1A Oumuamua, 2I Borisov, and 3K Atlas. The emergence of multiple detections in such a short interval has transformed scientific expectations. Models once predicting extremely low visitation rates have been recalibrated to reflect a galaxy densely populated with stellar ejecta, possibly trillions of such objects per cubic parsec. In this context, the arrival of 3I Atlas is not shocking but statistically plausible. Still, the resource Atlas is distinct in several important ways. Unlike Oumuamua, whose brief visibility produced more questions than answers, 3I Atlas was detected earlier in its inward trajectory and can therefore be studied more comprehensively. Unlike 2I Borisov, whose behaviour closely resembled that of a typical solar system, Comet 3 Atlas exhibits chemical and dynamical signatures that challenge existing models. One of the most significant anomalies lies in its chemical composition, particularly the early detection of carbon dioxide at large heliocentric distances and the unusual ratios of nickel to iron in its outcast material. In familiar comets, nickel and iron commonly appear in roughly equal proportions due to their parallel formation pathways in stellar environments. The detection of nickel without corresponding iron implies either an unusual formation environment or a mechanism of selective vaporization not yet understood. These findings invite questions about the diversity of comet-like bodies around other stars and whether conventional models of planetary system formation capture the full range of possibilities. Another point of scientific interest lies in the object's early activity. Comets typically begin vigorous outgassing only when they approach within a few astronomical units of the Sun, water ice. The dominant volatile in most solar system comets requires substantial solar heating to sublimate, but carbon dioxide sublimates at far lower temperatures, meaning that bodies rich in CO2 can develop comae much farther from the Sun. 3I Atlas began exhibiting activity at distances where water remains completely inert, suggesting that its surface ices differ markedly from those commonly observed in long-period comets. This activity in turn has implications for the object's brightness and observability. Comets with CO2-dominated comae can brighten more rapidly than expected, potentially leading to early discovery. Indeed, some simulations suggest that interstellar comets may be more detectable than previously assumed if they carry volatile inventories uncommon in the solar system. The early detection of 3I Atlas thus may hint at broader chemical diversity among extrasolar minor bodies. Despite its unusual chemistry, the most scientifically compelling aspect of 3I Atlas is its trajectory. Its hyperbolic orbit confirms its interstellar origin, but the details of its inclination and approach vector reveal further layers of interest. The object approaches from near the ecliptic plane, an alignment that is improbable but not impossible. If interstellar debris follows an isotropic distribution, arrivals from arbitrary angles should dominate. Yet several interstellar visitors have approached near the ecliptic, prompting discussions about observational bias. Survey telescopes more efficiently detect objects near the plane of the solar system, where both planets and many transient bodies pass. This bias provides a plausible explanation without invoking unusual coordination. If surveys focus disproportionately on the ecliptic, they will naturally discover more interstellar objects whose paths happen to align with it. Thus, what appears as a strange directional preference may simply reflect the geometry of current detection networks rather than any inherent preference in interstellar object trajectories. The intersection of 3I Atlas's path with the orbits of Mars, Venus and Jupiter offers additional opportunities for study but does not imply intentionality. Planetary approach distances depend on timing and geometry factors determined long before the object entered the solar system. While the near flyby of Mars provides a scientific windfall, allowing instruments in Mars orbit to collect unprecedented data, the alignment itself remains consistent with random, chance-given, sufficient observational timescales. Yet even while scientific interpretations remain grounded in physical principles, the confluence of events in 2025, 7 comets, an interstellar visitor, and a period of heightened solar activity reinforces the dynamic nature of the solar system. It reminds us that space is not a static void, but a region of constant motion shaped by long-range forces and populated by bodies whose paths intersect ours only briefly, before fading back into the vastness. The presence of 3I Atlas serves as a window into those broader galactic processes. It is a fragment of another world now passing through our own offering data that can refine existing theories of planetary formation, stellar chemistry, and the distribution of interstellar material. Whatever mystery its convergence with the comet swarm may evoke, the object ultimately expands our understanding of the solar system's position within a larger cosmic environment. By studying 3I Atlas alongside the 7 comet cluster astronomers, gain a rare opportunity to contrast local and interstellar bodies under similar conditions. It is in effect a natural comparative experiment, one that could not be deliberately arranged, but that nevertheless enriches our understanding of the diversity and dynamism of objects that traverse the Sun's gravitational domain. To understand the larger significance of the 2025 convergence, it is essential to consider the solar system not as a collection of isolated bodies, but as a dynamic, interconnected environment. Although planets, comets, and dust populations move according to well-established laws, they do so within a shared electromagnetic, gravitational, and heliophysical framework shaped by the Sun. This system is neither static nor uniform. It evolves through cycles of magnetic activity, solar wind variation, and long-term gravitational resonance. The behaviour of comets, whether born in distant reservoirs or arriving from interstellar space, cannot be understood without examining this broader context. At the centre of this environment stands the Sun's magnetic cycle, an approximately 11-year oscillation in which solar magnetic polarity reverses and magnetic complexity intensifies or relaxes. As the Sun approaches solar maximum, its activity increases across multiple dimensions. Sunspot formation intensifies, coronal mass ejections become more frequent, and high-speed solar wind streams emanate from long-lived coronal holes. These changes influence the heliosphere, the bubble of charged particles and magnetic fields that surrounds the solar system, and shape the conditions experienced by any object entering its domain. The year 2025 coincides with heightened solar activity, and this is not a trivial factor for understanding comet behaviour. As comets approach the Sun, the structure and intensity of their Comean tails depend not only on the sublimation of volatiles, but also on the interactions between outgassed material and the ambient solar wind. When the heliospheric environment is more energetic, dust tails become more pronounced. Ion tails become more structured and magnetic. Draping effects can induce complex filamentary patterns in the surrounding plasma. These interactions enhance visibility and increase the likelihood of detection by both ground-based telescopes and spaceborne instruments. In this sense, the apparent swarm of comets may be partially amplified by observational conditions. Under a calmer Sun, some of the 7 objects may have remained just above or below detection thresholds until reaching much smaller heliocentric distances. With stronger solar wind streams and elevated ultraviolet flux, however, Comets can brighten earlier and persist longer. This does not explain the timing of their orbital arrivals, but it does influence the intensity with which they manifest in observational data sets. The heliosphere also plays a crucial role in shaping the behaviour of interstellar objects whose interactions with solar radiation differ from those of long-period comets. Interstellar bodies enter the solar system at high velocities, carrying dust and volatiles unaccustomed to the Sun's spectral environment. Radiation, pressure, photoionization, and thermal gradients act on these materials in ways that reveal clues about their composition. For 3 Atlas, the early onset of CO2-driven activity, its rapid brightening and its unusual spectral emissions all reflect its exposure to the Sun's energetic radiation environment during a period of heightened solar output. Additionally, the solar system's gravitational architecture cannot be overlooked. Planetary alignments, though not causative in any mythic sense, influence the long-term stability of comet trajectories. Jupiter, whose mass dominates the gravitational landscape beyond the asteroid belt, acts as both a gatekeeper and a dispersal agent, capturing some comets while ejecting others into interstellar space. The 7 comets of 2025 each carry orbital signatures shaped by past encounters with Jupiter or Saturn, quiet gravitational interactions that occurred hundreds or thousands of years before their current inward journeys became visible. Meanwhile, interstellar objects such as 3I Atlas pass through this architecture on timescales too short for substantial perturbation. Their trajectories reflect only minor bending by solar gravity, unless they pass unusually close to a planet, as Oumuamua did with no significant interaction. Yet even small changes can be scientifically valuable, allowing astronomers to refine models of solar gravitational influence on high-velocity bodies and to compare interstellar responsiveness to local comet behaviour under similar conditions. Taken together, the 2025 convergence highlights the solar system's nature as a dynamic emergent environment, one where multiple phenomena, gravitational, electromagnetic, chemical and observational, interact to shape what we see and how we interpret it. The 7 comets are not coordinated, but they are all responding to similar environmental factors as they fall sunward. 3I Atlas is not directed by those same factors, but its behaviour is illuminated by them. The Sun, with its expanding and contracting magnetic fields, is the common background condition against which all these trajectories unfold. Understanding this interconnected system also provides a useful corrective to pattern-seeking instincts. The mind may be inclined to see intention or synchronization where none exists, especially when events cluster in ways that feel meaningful. But from a scientific standpoint, complexity does not imply coordination. The solar system is complex not because it is designed to communicate patterns, but because many processes operate simultaneously at different spatial and temporal scales. Nevertheless, the convergence of so many active bodies in a single year local and interstellar underscores the value of studying the solar system as an integrated whole. Observations of the comet swarm combined with detailed spectroscopic and dynamical analyses of 3I Atlas provide an unusually rich dataset for understanding how diverse small bodies react to the same heliophysical environment. They also invite broader investigations into how the solar system interacts with the galaxy beyond it, and how interstellar material traces paths that occasionally intersect with our own. In this way, the 2025 convergence is scientifically meaningful, not as a coordinated event, but as a window into the complex interplay of forces that shape the solar system's evolving structure. To place the 2025 convergence into proper context, it is necessary to examine the larger heliophysical environment in which it is unfolding. While comet trajectories are governed primarily by gravity, their visible behaviour, comets, tails, fragmentation events, and sudden outbursts is strongly shaped by the Sun's changing energetic output. As the Sun ascends toward the peak of its 11-year magnetic cycle, the solar system becomes a more dynamic and electrically active place. Comets, fragile and porous in their constitution, become sensitive instruments, recording the invisible weather of interplanetary space. Solar maximum marks the phase in which the Sun's magnetic polarity reverses, and magnetic field lines become more tangled and unpredictable. Sunspot numbers increase, solar flares become more common. Coronal mass ejections erupt with greater frequency, sometimes launching billions of tons of charged plasma into space. The solar wind itself, the Sun's continuous outflow of charged particles, becomes faster, denser, and more structurally complex. This environment fundamentally alters how comets behave as they enter the inner solar system. When solar activity rises, comet ion tails become more pronounced and more reactive. The blue filamentary ion tail, a stream of charged particles being swept away from the comet's nucleus, aligns itself with the direction of the interplanetary magnetic field. During calm periods, this tail appears smooth and predictable. But during solar maximum, when magnetic field variations propagate outward from the Sun at hundreds of kilometers per second, the ion tail can undergo dramatic contortions. It can twist, kink, fold back on itself, or if the magnetic polarity suddenly reverses, disconnect entirely, leaving a detached segment drifting alone while a new tail forms into its place. These tail disconnection events have been documented for decades. but they become far more frequent during years of elevated solar activity. For inexperienced observers, the sudden disappearance of a comet's tail or the simultaneous deformation of several tails across the night sky can appear coordinated, almost deliberate. But to solar physicists, these are natural signatures of an energized heliosphere, visual reminders that magnetic structures invisible to the naked eye are sweeping through interplanetary space like storms. Dust tails behave differently. Unlike ion tails, which respond to electromagnetic forces, dust tails are shaped by radiation pressure. Solar photons exert momentum when they strike dust grains. Under normal circumstances, this produces the iconic sweeping curved tail that glows faintly under reflected sunlight. But during solar maximum enhanced ultraviolet radiation can break down dust particles more rapidly, or charge them differently, altering how they respond to radiation pressure. The result is a more dynamic dust tail one that shifts and broadens as the comet rotates and as radiation from the sun fluctuates. Thus, the year 2025 offers a unique observational environment, not simply because several comets are inbound, but because the solar system around them is unusually active. The effects of solar maximum extend beyond comet behaviour. Earth too becomes a participant in this heightened heliophysical environment. As the solar wind buffets Earth's magnetic field, geomagnetic storms become more frequent, leading to intensified auroras at latitudes far lower than usual. In such years, observers in regions that rarely see auroral activity, northern Europe, the northern United States, parts of China, may witness curtains of green and red shimmering overhead. These events are terrestrial analogues to the tail disturbances experienced by comets. Both are responses to the same solar inputs. Meanwhile, in near-Earth space, satellites experience increased radiation exposure. Solar energetic particles can penetrate shielding, induce charging effects, or interfere with onboard electronics. Communications blackouts, GPS anomalies, and sensor disruptions are more common during solar maximum. Aviation routes over the poles must sometimes be altered to avoid excessive radiation doses to passengers and crew. All of these effects unfold against the same backdrop as the comet swarm, creating a layered sense of celestial intensity. To the public, the simultaneous appearance of bright comets, unusual auroras, and occasional technological disruptions can feel like part of a single interconnected pattern. But scientifically, these phenomena arise from shared solar causes rather than direct interactions among the objects themselves. This distinction is critical. The synchronized behavior of natural systems under common external influence can easily be misinterpreted as intentional coordination. The human mind evolved to detect patterns even at the risk of seeing connections where none exist, because in ancestral environments, the cost of missing a real pattern outweighed the cost of assuming a false one. In a thunderstorm, when multiple trees sway together, one might imagine a hidden force directing them in unison. In truth, they are simply responding to the same wind. In 2025, the wind is the solar maximum itself, an energetic, magnetically complex phase that shapes the behavior of every comet, every dust grain, every magnetized structure within the heliosphere. Interstellar objects such as 3 Aesios Atlas respond to this environment in their own distinct ways. Their materials forged beyond the sun's influence may outgas at different thresholds or break apart under different thermal stresses. Their ion tails, shaped by volatiles uncommon in local comets, may display rare colours or structures under the influence of the solar wind. The early activity reported for 3I Atlas, even at large solar distances, suggests the presence of supervolatile materials, compounds such as CO or CO2 that sublimate under much weaker heating than the water ice typical of traditional comets. As solar maximum intensifies, these volatiles will respond even more strongly, potentially revealing chemical signatures never before observed in a comet passing through the inner solar system. For planetary scientists, this represents a rare opportunity, a chance to study material from a distant stellar nursery under controlled measurable conditions. The heliospheric environment thus becomes not merely a backdrop, but an active participant in shaping the scientific value of the 2025 convergence. While the comets themselves were set on their paths long ago, the sun's current state transforms their arrival into a richer, more revealing observational moment. With the sun at full intensity, The stage is set not for cosmic coordination, but for unprecedented visibility, enhanced scientific value, and deeper understanding of how small bodies respond to the forces that govern the inner solar system. In this sense, solar maximum acts as a lens. It does not change the underlying reality, but it magnifies it, revealing interactions and structures that might otherwise remain hidden. As the solar system enters a year of heightened heliophysical activity, Earth becomes not merely an observer of celestial dynamics, but an active participant in them. The same forces that sculpt the tails of comets shape the electromagnetic environment around our planet, influencing technologies, navigation systems, and even the rhythms of the ionosphere. To understand why the 2025 comet swarm has captured the public imagination so profoundly, we must first explore how these terrestrial effects arise, and how easily they can be confused with deeper, more sinister cosmic patterns. Space weather begins at the Sun, but its effects cascade outward in ways that touch nearly every corner of modern life. When a large coronal mass ejection erupts from the solar surface, it launches a wave of plasma and magnetic field structures through interplanetary space. If this wave happens to intersect Earth, the consequences can be dramatic. The planet's magnetosphere, normally a stable shield that diverts charged particles around the atmosphere, becomes compressed and distorted. This triggers geomagnetic storms that ripple across continents like invisible tides. The impacts of these storms manifest through physics both simple and profound. As magnetic fields fluctuate, electrical currents are induced in long conductors, including power lines, pipelines, and undersea cables. Under the right conditions, these induced currents can overload systems and trigger widespread power failures. The famous 1989 Quebec blackout is a reminder that even a modest geomagnetic storm can affect millions of people in minutes. The more intense storms of solar maximum years bring similarly heightened risks. Meanwhile, satellites orbiting above Earth's atmosphere confront an even harsher environment. High-energy protons can penetrate electronic systems, temporarily disabling sensors or causing bit flips in memory modules. Communication satellites may experience signal degradation as the ionosphere thickens and shifts. GPS accuracy suffers. Aircraft flying near the poles must sometimes divert to lower latitudes to avoid increased radiation exposure. All of this unfolds behind the scenes, far removed from the nightly dance of comets above, but intertwined through common solar origins. In such a context, correlations can feel charged with meaning. When a cluster of comets brightens, when auroras ripple overhead, and when navigation systems experience anomalies, it is easy to imagine a single cause tying them together. But scientific analysis reveals that these effects arise largely from the sun cycles, not from the comets themselves. Still, the human mind resists such compartmentalization. The tendency to attribute connected meaning to temporally aligned events is one of the oldest cognitive patterns we possess. Our ancestors survived by detecting relationships between environmental cues. A shift in the wind might signal a predator's approach. An unusual cloud could predict a coming storm. The brain evolved to seek patterns because the cost of ignoring a real one was catastrophic. This evolutionary heritage remains with us today. When 7 comets approach the inner solar system at once, an undeniable statistical rarity, the instinctive response is to search for orchestrators, messages, or hidden mechanisms. And when this celestial clustering coincides with a solar maximum capable of disrupting global infrastructure, the impression of cosmic choreography becomes even more compelling. The danger lies not in curiosity, but in conflating correlation with causation. Scientific method offers tools to disentangle these relationships. Superposed epoch analysis allows researchers to test whether infrastructure failures cluster around specific celestial events more frequently than chance predicts. Cross-correlation functions can assess whether unusual comet behavior aligns with specific solar parameters, such as solar wind speed or interplanetary magnetic field orientation. Magnetometer arrays distributed across the globe provide precise temporal maps of geomagnetic disturbances that can be matched directly to solar storm arrival times. These methods reveal a consistent truth: comets do not disrupt power grids, scramble navigational systems, or shape auroras. The sun does. Yet the comets play a more subtle role, not as causes of terrestrial phenomena, but as mirrors of the solar system's energetic state. Their tails act like celestial seismographs, sensitive tracers of magnetic and plasma conditions that would otherwise remain invisible. When the heliosphere grows, turbulent, comets reveal that turbulence in real time. They make the invisible visible. In earlier eras before the development of plasma physics and magnetohydrodynamics, humans interpreted these signs symbolically. A bright comet followed by a famine or political upheaval seemed to encode cosmic commentary on human affairs. Even today, cultural memory retains echoes of that interpretive impulse. But modern science provides a more grounded understanding. The apparent simultaneity of cometary displays and earthly disturbances arises from shared influence, not mutual interaction. A key principle in evaluating extraordinary claims is the alignment of timescales. Geomagnetic storms follow predictable patterns based on solar rotation and solar wind propagation. If a technological failure occurs during the arrival window of a known solar storm, the causal chain is well understood. If such failures were instead linked to specific comets, the correlations would be irregular, inconsistent, and disconnected from heliophysical markers. To date, no such comet-linked pattern has emerged. Instead, the data consistently point towards solar drivers as the dominant force. Nevertheless, the psychological effect of seeing multiple cosmic events unfold simultaneously should not be underestimated. Humans interpret celestial patterns not only through logic, but through narrative. A sky filled with comets during a year of technological vulnerability feels different from a sky hosting a single faint tail during a quiet solar cycle. The coincidence may be natural, but its resonance, its emotional weight is very real. This is perhaps the deeper explanation for why the 2024 fifth convergence has sparked so much public fascination. It is not simply a cluster of comets, it is a cluster of experiences, strange lights in the sky, auroras near the equator, disruptions in communication, the mysterious presence of an interstellar visitor. Together these form a story that the human mind cannot help but assemble. Yet science reminds us that stories and causes are not the same. The task of astronomy is to understand, measure and interpret without assuming intent. The comets arriving in 2025 trace orbits set in motion long before human civilization existed. The solar storm cycles were unfolding long before the first telescopes. The convergence of these phenomena is striking, but it remains a convergence and intersection of independent processes shaped by cosmic rhythms older than humanity itself. Thus, the illusion of coordination dissolves under scrutiny, replaced by a more profound realization: the universe does not need to send messages for its patterns to be meaningful. Meaning arises from observation, from the act of watching the sky and searching for our place within it. Among all the celestial bodies entering the inner solar system in 2025, none has captured scientific attention more profoundly than 3I Atlas, the third confirmed interstellar object ever observed. Its presence alters not the physics of the comet's swarm, but the context in which we study it. Unlike the traditional comet's icy relics from the Oort cloud, 3I Atlas was forged in the gravitational well of another star. Its chemistry, motion and behaviour represent a message inscribed across stellar distances, carried through interstellar darkness for millions of years, before arriving here now during one of the most comet-rich years in recent memory. To understand why this object matters scientifically, one must first consider the geometry of its trajectory. Unlike elliptical comets bound to the Sun, interstellar objects trace hyperbolic orbits paths that curve inward, once swing around the star, and then depart forever. Their hyperbolic excess velocity, the leftover speed they retain even after escaping the Sun's gravity, reveals the kinetic imprint of their birthplace. 3I Atlas carries this imprint like a fossil. Its speed, angle of approach and inclination encode ancient gravitational histories from another stellar system. The object approaches the solar system from a direction near the constellation Perseus, descending toward the ecliptic plane at a modest angle rather than plunging in steeply from above or below. This detail matters. The ecliptic, an imaginary plane containing most of the planet's orbits, functions as a vast gravitationally sculpted sheet. Most solar system bodies lie within a few degrees of this plane. For an interstellar visitor to pass so near, it is statistically uncommon. Yet uncommon is not the same as orchestrated. Geometry alone cannot imply intent. Instead, the near-ecliptic path provides scientists with an opportunity. It places 3I Atlas in regions of space where comparisons with local comets become meaningful. The object will experience similar solar radiation, similar solar wind conditions, and similar gravitational architecture as its solar-born counterparts. This permits direct comparison how interstellar materials respond to familiar forces and how they diverge from the behaviour of native comets. One key puzzle emerged early. Even at distances where water ice remains completely inert, 3I Atlas displayed premature activity, a diffuse coma, a faint but distinct tail. This suggests the presence of supervolatiles compounds like carbon monoxide or methane that sublimate at far lower temperatures than water. Such volatiles are rare in most solar system comets, either depleted over time or buried deep beneath insulating layers. Yet in an interstellar environment, colder, quieter, more chemically diverse, these materials can persist for billions of years. Thus, 3I Atlas serves as a probe not only of space but of time. Its interior composition reflects chemical conditions in the region where it formed perhaps a cold, distant belt around another star, or even the debris of a disrupted protoplanetary disk. Its activity curve as it approaches the Sun becomes a kind of experiment, a live test of how alien materials respond to solar heating. The object's retrograde motion adds another layer of intrigue. While most solar system bodies orbit counterclockwise when viewed from above Earth's north pole, 3I Atlas travels in the opposite direction. This creates unusually high relative velocities during its passage. High-speed objects spend minimal time within gravitational influence zones, reducing the likelihood of significant gravitational perturbations. For this reason, even though the interstellar visitor moves through regions populated by the incoming comets, meaningful interactions are physically improbable. Still, the timing raises philosophical questions. Why now? Why during this extraordinary convergence of 7 comets and a solar maximum? Scientists answer cautiously. Coincidence is both the simplest and the most statistically supported explanation. Interstellar objects arrive irregularly, and detection capabilities have improved dramatically in recent years. Many would have passed unseen a century ago. But coincidence does not diminish scientific value. Interstellar objects represent the only physical samples humanity has ever observed from beyond the Sun's gravitational domain. If meteorites are history books of the early solar system, then objects like 3I Atlas are history books from neighbouring stellar nurseries, fragments of other timelines, other chemical pathways, other cosmic origins. Their mere presence redefines the scale of what is accessible to study. 3I Atlas's chemical fingerprint when captured through spectroscopy during perihelion may reveal isotopic ratios unlike any found in solar system materials. Differences in deuterium content carbon ratios or noble gas distributions could illuminate the physical conditions of a distant star's protoplanetary disk. Such comparisons would deepen our understanding of how planetary systems form, how they differ, and how common or rare our own chemical history might be. Some researchers speculate that an interstellar object passing through the solar system during a year of intense comet activity might serve as an indicator rather than a cause. Perhaps the gravitational architecture of the outer solar system undergoes periodic shifts, subtle, slow perturbations causing both inbound comets and increased likelihood of intercepting drifting interstellar debris. This remains speculative, but it is a line of inquiry grounded in physical plausibility rather than imagination. Ultimately, 3I Atlas symbolises something deeper, the quiet reminder that our solar system is not isolated. It is porous. It exchanges material with the galaxy. Across millions of years, countless fragments of distant worlds pass through our space, unnoticed, unmeasured, unseen, until one aligns with our brief moment of technological capability. In 2025, we are prepared. We can measure, compare, and learn. And in doing so, we confront a humbling truth: the universe is not static. It breathes, exchanges, circulates. Comets arrive. Visitors pass through. The sun brightens and storms, and we observers on a small world interpret, question, and seek coherence, not because the cosmos is sending messages, but because meaning is how humans navigate immensity. As 3I Atlas draws closer to the Sun, it approaches the stage that astronomers understand as the true test of a comet's identity perihelion, the moment of closest solar approach. Every comet, whether born in the Oort cloud or ejected from a distant star, must pass through this crucible. It is here that chemical composition, structural integrity, and thermal resilience are revealed with unfiltered clarity. For an interstellar visitor, perihelion is something more a rare experiment in stellar cross-interaction, where material shaped under a foreign sun is exposed to the physics of ours. The physics that govern perihelion are simple yet profound. Solar radiation increases by the inverse square of distance, doubling in intensity each time the separation is halved. What was once a gentle warming in the outer system becomes within the inner AU a torrent of photons, heat, and solar particles. The surface of the comet responds first. Volatile ices transition directly into gas, creating jets that erupt from the nucleus like vents on a primordial world. These jets sculpt the coma, alter the light curve, and in some cases produce small but measurable thrust that nudges the comet's trajectory. For 3I Atlas, the stakes are uniquely high. Its early activity at unusually distant ranges suggests that low-temperature volatiles, carbon monoxide, methane, nitrogen compounds lie abundantly within its structure. As perihelion approaches, these volatiles will experience dramatic sublimation. Spectroscopic observations will have an opportunity to detect emission signatures never before observed in a solar environment. These signatures could reveal exotic ices preserved since the formation of another star system, untouched by heat for millions of years. This is why astronomers speak of perihelion not merely as a milestone, but as a moment where an object speaks its chemistry aloud. The coma that forms around 3I Atlas will act as a diagnostic instrument. Variations in brightness will mark transitions between different volatiles. Sudden outbursts will reflect structural cracking or the collapse of subsurface cavities. Dust grains released at this stage will tell researchers about the size distribution and mineral content of the comet's interior. If the object contains compounds rare or unknown in solar system comets, these materials will reveal themselves through specific absorption or emission lines. The formation of tails during perihelion adds another layer of scientific insight. A comet typically produces two, the ion tail, shaped by the solar wind and interplanetary magnetic field, and the dust tail shaped by radiation pressure. For an interstellar visitor, each tail provides a different category of clues. The ion tail may show unusual coloration or ionization states if the volatiles differ sharply from solar native materials. The dust tail may contain grains with reflectance properties distinct from those of Oort cloud comets. But perihelion also brings risk. Comets are fragile objects, porous, low-density aggregates of dust and ice held together by gravity weaker than a handshake. As the nucleus rotates under uneven heating, internal stresses accumulate. Cracks propagate. Jets erupt asymmetrically. In some comets, these forces reach a threshold where the nucleus literally tears apart. This fragmentation, dramatic as it appears, is not a failure but a revelation. When a comet splits, fresh interior material is exposed material untouched since the birth of the object itself. For 3 Atlas, fragmentation would offer unparalleled access to truly pristine interstellar material. It would allow astronomers to analyze deeper chemical layers and compare them with the outer crust. Certain volatiles might be trapped at depths unreachable under normal sublimation. Spectroscopic surveys could capture these compounds before they dissipate. Yet fragmentation would also complicate the object's observed trajectory, making attempts to detect subtle orbital anomalies far more difficult. Multiple fragments, each following slightly different paths, would introduce noise into measurements. For researchers attempting to test for hypothetical correlations between 3I Atlas and the 7 comet swarm, the complexity introduced by breakup would require recalibrations and new models. Still, whether 3I Atlas remains intact or splits into several pieces, perihelion will be the moment when the object becomes most scientifically legible. In parallel with these processes, the Sun's own condition approaching the peak of solar maximum will amplify every observable feature. Enhanced ultraviolet radiation will increase ionization rates, making the ion tail more visible. Stronger solar wind variations will influence tail directionality, introducing dynamic structures that reflect the heliospheric environment. If coronal mass ejections strike the region through which 3I Atlas travels, its tail could undergo sudden transformations, creating dramatic visual signatures that blend interstellar chemistry with solar activity. This interplay underscores the deeper lesson of perihelion that comets are not isolated travellers, but participants in a vast interconnected system. Their behaviour is shaped not only by their internal structure, but by the dynamic environment that surrounds them. For astronomers, the upcoming perihelion is not simply an event. It is an opportunity, a rare convergence of interstellar material-enhanced solar activity and unprecedented observational capability. Ground-based observatories, space telescopes, and distributed networks of amateur astrophotographers will collectively record the evolution of 3I Atlas in extraordinary detail. Every frame, every spectrum, every light curve will contribute to a scientific narrative stretching beyond the boundaries of the solar system. And for the broader public, perihelion represents the most luminous moment in an unfolding story that blends curiosity, uncertainty, and cosmic scale. It reminds us that even in an age of technology, there remain phenomena that resist prediction and invite humility. The Sun will test 3I Atlas in the same way it has tested every comet before it. Some emerge brighter, some fracture into temporary beauty, some fade quietly into darkness. Whatever happens, perihelion will reveal what lies beneath the surface, both literally and metaphorically. The crucible awaits. As the Sun approaches the peak of its magnetic cycle, the entire inner solar system becomes a stage shaped by forces invisible to the eye, but unmistakable in their influence. Every comet now entering this region moves through an environment more energetic, more turbulent, and more expressive than usual. Sunspots cluster along the solar surface magnetic fields, twist into unstable knots, and coronal mass ejections surge outward like tidal waves of plasma. Within this charged environment, the comets of 2025 do not simply drift, they react, each becoming a sensitive instrument that records the changing conditions of the heliosphere. The ion tails, composed of gases stripped and electrified by the Sun's radiation, respond immediately to fluctuations in the interplanetary magnetic field. A slight shift in magnetic polarity can pull a tail sideways. A stronger disturbance can tear it away completely, leaving a detached filament drifting through space as a new tail begins to form. These tail disconnection events, though dramatic, are natural expressions of plasma physics. When several comets experience them within the same week, the coincidences can feel choreographed, yet the explanation remains simple. The same solar disturbance is sweeping past each of them in turn. The dust tails, influenced not by magnetic fields, but by radiation pressure, also become more expressive during solar maximum. Increased ultraviolet output alters how particles absorb heat, how they scatter light, and how they are pushed outward from the nucleus. Fine dust accelerates rapidly under intense photon pressure, creating broad, fan-like tails, while heavier grains lag near the comet's orbital track. For an observer watching the night sky, these sudden changes in brightness or structure can appear as if several comets are responding to a shared cue. They are, but the cue is the Sun, not a hidden cosmic conductor. On Earth, the same solar impulses shape phenomena entirely separate from the comets, yet visually and emotionally intertwined. Geomagnetic storms triggered by the same solar winds that sculpt comet tails bring auroras into lower latitudes. People far from the poles, those who rarely see the sky painted green or red, may find themselves watching a bright comet framed by shimmering curtains of light. Such alignments feel intentional, almost symbolic, and it is easy to imagine a message encoded in the sky. But the correlation is physical, not metaphysical. Both the comet and the aurora are responding to the same solar pulse. The presence of 3I Atlas adds another layer of complexity to the year's observations. As an interstellar object, its materials may interact differently, with the energized solar wind producing spectral colors or ionization patterns rarely seen in local comets. Its dust tail, influenced by foreign chemistry and intense ultraviolet radiation, may reveal structures unfamiliar to observers. While these distinctions will undoubtedly capture attention, they arise not from purposeful behavior, but from the natural responses of alien materials meeting an active Sun. For scientists, this combination of multiple comets and heightened solar activity creates an unprecedented research opportunity. Comets arriving under nearly identical heliophysical conditions allow for comparative studies of volatile content dust emission patterns and tail formation dynamics. Researchers can examine how cometary jets respond to changes in solar wind density, how dust distributions differ under intense ultraviolet radiation, and how ion tails behave when exposed to rapidly fluctuating magnetic fields. Such synchronized forcing conditions are extraordinarily rare. One might wait decades for a similar natural laboratory. These scientific benefits arise precisely because the comets are not coordinated. Their independence strengthens the validity of comparisons. If Pan-STARRS Swan, Stereo Atlas, K1 Atlas, G3 Lemon and Neat each respond differently to identical solar conditions, those differences reveal their intrinsic properties, compositions, porosities, histories, not some underlying cosmic intention. The Sun provides the controlled variable. The comets provide the diversity. The research emerges from the intersection. Yet understanding the physics does not diminish the wonder of witnessing these events. Humans are creatures of narrative, and the sky is one of our oldest storytellers. When several tails bend in the same direction, we perceive alignment. When multiple comets brighten within the same month, we sense rhythm. When an interstellar object passes through during a year of unusual activity, we search for meaning in the coincidence. This interpretive impulse is ancient, older than astronomy itself, and it adds emotional depth to moments of scientific clarity. It is natural to feel awe in the face of such timing, but the true beauty lies in how the pieces fit together without needing hidden intention. The comets follow paths set into motion millions of years ago. The solar cycle evolves according to magnetic laws older than human history. Our instruments' sensitive cameras, spectrographs, magnetometers allow us to perceive their interactions with unprecedented detail. The universe is neither signaling nor warning. It is simply being observed with a precision never before possible. In this sense, the 2025 convergence becomes a celebration not of cosmic message, but of cosmic accessibility. We are watching the sun shape the comets, and the comets illuminate the sun. We stand at a moment where natural processes align just enough to let us see their relationships clearly. And in that clarity, meaning arises not imposed by the universe, but created by our understanding of it. When space weather intensifies, its effects ripple far beyond the delicate tails of comets. Earth, wrapped in its magnetic cocoon, responds with its own set of luminous, disruptive and occasionally unsettling phenomena. The same charged particles that sculpt iron tails in deep space also cascade into Earth's magnetosphere, triggering geomagnetic storms that can reshape the behaviour of our technological environment. In the 2025 comet year, these terrestrial responses will become especially visible, and their timing overlapping with multiple bright comets may tempt many to conclude that something cosmic is reaching toward us. But the true explanation remains anchored in the physics of the sun, not the intentions of the sky. A geomagnetic storm begins when a surge of solar particles slams into Earth's magnetic field, compressing it, and inducing electric currents through the planet's ionized boundaries. Though invisible in the vacuum of space, these currents can generate powerful consequences on the ground. Long transmission lines spanning hundreds of kilometers act as antennas, picking up induced electrical flows that transformers were never designed to handle. Under the right conditions, these surges can trigger cascading failures, as they did in March 1989 when Quebec's power grid collapsed within 90 seconds of a solar shock. Similar vulnerabilities exist today, though our monitoring systems have improved. During solar maximum, these storms occur more frequently, raising the odds that some infrastructure failures may coincide with bright cometary activity. A blackout or communication disruption during a night when a comet glows overhead creates an illusion of cosmic agency. The sky brightens, the ground darkens, and coincidence feels like connection. Yet geomagnetic storms obey predictable solar mechanics. Their timing corresponds closely to solar flare events, solar wind propagation speeds, and the alignment of Earth with specific magnetic sectors, not to the orbital paths of comets, drifting tens of millions of kilometers away. In near-Earth, orbit satellites face their own hazards. Solar energetic particles penetrate shielding corrupt memory modules and occasionally shut down sensors. GPS accuracy suffers under ionospheric disturbances. Weather satellites may send corrupted data. Communications may weaken or drop entirely. For the thousands of satellites now circling Earth, 2025 will be a year of intermittent challenge, and each anomaly will occur under the same sky that hosts the comet swarm. The resulting narrative for those inclined toward patterns practically writes itself: a sky full of comets, a sun full of storms, and a web of satellites flickering like nervous fireflies. Air travel too feels the influence. At high latitudes where Earth's magnetic field channels radiation more directly into the atmosphere, commercial aircraft must sometimes reroute to avoid exposing passengers and electronics to heightened radiation levels. Flight paths shift southward. Radio communication bands fluctuate. Pilots may experience temporary loss of HFE signals. Again, these changes occur independently of any comet, yet the impression of planetary vulnerability grows stronger when the heavens are unusually active. This psychological environment is fertile ground for misattribution. Humans are inherently meaning-making beings. We draw connections instinctively, especially when confronted with simultaneous extraordinary events. Multiple bright comets, unusual auroras, navigation anomalies, and solar disturbances blur together into a single emotional experience. People sense coherence, even when the underlying mechanisms remain distinct. This impulse is understandable throughout history. Celestial patterns accompanied periods of social uncertainty. Comets were recorded before plagues, earthquakes, wars, and political upheavals, not because they caused these events, but because chroniclers remembered them more vividly during troubled times. Modern data, however, offers a clearer lens. Sophisticated monitoring networks track solar activity with precision unimaginable to earlier generations. The Space Weather Prediction Center issues alerts based on real-time observations of solar flares, coronal mass ejections, and plasma density variations. Magnetometer arrays across the globe record geomagnetic changes to the minute. Radio operators detect disturbances in propagation patterns long before the general public becomes aware. With these tools, scientists can trace nearly every technological anomaly to solar origins rather than celestial symbolism. Yet even with this clarity, coincidences inevitably occur. A power grid issue during the arrival of Pan-stars might feel prophetic. A GPS disruption during Swan's brightening could seem orchestrated. A geomagnetic storm aligning with Three-Eye Atlas's approach may trigger conspiracy theories. The statistical likelihood of coincidental overlap increases during solar maximum simply because more storms occur. The more frequent the solar disturbances, the greater the chance they will share the sky with a bright comet or several. The task for science is not to minimize wonder, but to disentangle causes from correlations. It requires recognizing that multiple independent phenomena can unfold simultaneously without sharing a deeper connection. Solar wind propagates from the Sun to Earth over predictable timescales. Comet trajectories evolve over millions of years. Technological vulnerabilities respond to electromagnetic physics. When these domains intersect in time, no hidden message is implied. Instead, what emerges is a portrait of a solar system alive with interacting systems, each operating under its own principles, yet shaped by the Sun's overarching influence. And perhaps there is a different kind of meaning in this realization. Not a warning encoded in comet tails nor a cosmic signal sent through auroras, but a reminder of how deeply our world is intertwined with the star that sustains it. The Sun does not communicate intentionally, yet its storms can darken continents. The comets do not coordinate, yet their synchronized vulnerabilities reveal the same invisible forces shaping their fates. The universe does not speak in omens, yet its rhythms remind us how small and porous our systems truly are. To live during a year when these rhythms overlap is to witness the solar system's complexity made visible, not as prophecy but as physics, not as threat but as evidence that we inhabit an environment more dynamic, more connected and more fragile than we often realize. Throughout human history, the appearance of bright comets has triggered a profound and instinctive reaction, an emotional fusion of awe, fear, and anticipation. Long before spectroscopy and orbital mechanics allowed us to understand their true nature, Comets were interpreted as celestial signals, heralds of change, warnings from the heavens, or harbingers of upheaval. This tradition stretches across civilizations from ancient China to medieval Europe, from the Maya world to the classical Mediterranean. When several comets appeared at once, the effect was magnified, stirring entire societies into reflection or alarm. In 2025, as 7 comets converge with an interstellar visitor, echoes of that ancient psychology rise once again, even as science offers clearer explanations than any available to previous generations. Ancient Chinese astronomers recorded comets with extraordinary precision, linking their appearances to political transitions, droughts, or military victories. These interpretations were not irrational. They emerged from patterns observed through the lens of surviving memory. When a dramatic celestial event occurred near a time of terrestrial unrest, the human mind forged connection. Medieval chroniclers in Europe did the same. The comet of 1066 became forever associated with the fall of the Anglo-Saxon kings, not because it caused the political shift, but because its presence made the moment feel cosmically significant. In their eyes, the sky was not a passive backdrop, it was a participant in history. Even during the Enlightenment, when Newtonian physics began eroding the mythology around comets, cultural narratives remained powerful. When Halley's Comet returned in 1758, it coincided with geopolitical tension, and many interpreted its reappearance as a symbol either of destruction or renewal. People saw meaning because meaning was comforting. A sky that reacts to human events feels less indifferent than one governed entirely by impersonal laws. This persistent desire for cosmic symbolism survives into the modern era, enhanced rather than diminished by our technology. In the age of social media, narratives spread not through royal courts or religious texts, but through global platforms optimized for engagement. A bright comet photographed with a dramatic soundtrack, a time-lapse of multiple tales bending simultaneously, or a speculative theory dressed in pseudo-scientific language can ignite public imagination far more quickly than peer-reviewed data ever could. The online world rewards emotional clarity, not analytical rigor. And so, as the comet swarm of 2025 takes shape, millions turn to stories that echo ancient instincts, that something is being signalled, that patterns are purposeful, that the sky is somehow aware of us. The presence of 3-Eye Atlas intensifies this effect. An interstellar visitor carries symbolic weight even for scientifically trained minds. It embodies distance, otherness, and the unknowable. When such an object arrives during a year already filled with unusual celestial activity, cognitive patterns hardwired into human psychology activate powerfully. We look upward and see not coincidence, but choreography. Yet science teaches a subtler truth: coincidence, and meaning can coexist without causation. The universe has no need to intend in order to inspire. Understanding this psychological landscape is essential for communicating astronomy responsibly. When people encounter dramatic sky events, emotional responses often precede logical ones. Fear, wonder, and uncertainty blend into a narrative long before data enters the conversation. This does not make the public unreasonable, it makes them human. The task for science, then, is not to dismiss these impulses, but to guide them gently toward interpretations grounded in measurable reality. The comet swarm illustrates how difficult this can be. Multiple rare events occurring within a short span naturally feel interconnected. The appearance of new visitors, the shimmering rise of auroras, the disruptions of satellites, the heightened awareness of solar storms all create an overwhelming sensory environment. In past centuries, these patterns would have become religious narratives. Today they become internet speculation about hidden forces or coordinated cosmic signals. And while the language has changed, the underlying psychology has not. This is why scientific communication must emphasize the difference between improbable and impossible. Rare events occur naturally in a universe governed by vast timescales and enormous populations of objects. When millions of comets exist, some clusters are inevitable. When solar cycles repeat every 11 years, some storms will align with celestial displays. When technology permeates our lives, some failures will coincide with astronomical phenomena. It is the human mind, not the cosmos, that binds these elements into a single story. Yet there is a quiet value in recognizing this tendency. The desire to see significance in the sky reflects a deeper truth about humanity's relationship with the universe. We long for connection. We want to believe that the cosmos notices us, that our presence resonates beyond our atmosphere. The scientific perspective can feel cold in comparison, emphasizing randomness and physical law over symbolism. But within the scientific worldview lies another kind of wonder, one grounded not in destiny, but in discovery. The fact that we can measure comet composition across millions of kilometers, track interstellar objects with precision, and understand solar storms with mathematical clarity is itself astonishing. Knowledge does not diminish mystery, it transforms it, and so as the comets of 2025 brighten the sky, the challenge is not to suppress the ancient impulse to interpret, but to refine it. The universe does not send warnings, but it does provide opportunities for insight. It does not communicate through omens, but it does reveal patterns worth studying. The 7 comets are not coordinated, yet their convergence gives us a rare chance to deepen our understanding of solar system dynamics. The interstellar visitor carries no message, yet its presence lets us study chemistry shaped under a different sun. The true message, if one exists, is that our species has reached a point where the sky can be observed with clarity, not fear. That we can distinguish mythology from physics without losing our sense of wonder. That we can hold 2 truths at once: the cosmos is indifferent, and yet its beauty moves us deeply. Artificial origin, few ideas inspire as much fascination, debate, and quiet fear as the suggestion that an interstellar visitor might not be a natural fragment of a distant star system, but an engineered artifact. When an object like 3I Atlas enters our solar system, at the same moment that 7 bright comets appear, the human mind instinctively gravitates toward narratives of design. Coordination feels more compelling than coincidence. Agency feels easier to comprehend than randomness. But the scientific method demands that fascination be tempered with measurement, and that extraordinary claims be supported by evidence capable of withstanding skeptical examination. The question is not whether an artificial origin is possible in principle, but whether the observed characteristics of the 2025 objects require such an explanation. To evaluate the alien hypothesis meaningfully, we must consider what artificiality would look like in physical terms, not in cinematic tropes or speculative fiction, but in the language of spectroscopy, orbital mechanics, and material science. An artificial interstellar probe, if one existed, would almost certainly contain refined metals, engineered alloys, or composite materials with spectral signatures distinct from those of natural ices and silicates, even microscopic traces of processed elements. Aluminum alloys manufactured titanium structures. Synthetics not formed in astrophysical environments would produce emission or absorption lines, unlike any found in ordinary comet spectra. 3I Atlas, however, displays the faint broad band spectral features consistent with volatile ices sublimating under solar radiation. Nothing in its observed chemical profile so far suggests the presence of engineered materials. It behaves in composition like an ice-rich object forged in the cold outskirts of a planetary system alien, only in origin, not in intent. Orbital behavior offers a second test. A probe under active control would exhibit non-gravitational accelerations inconsistent with sublimation patterns or precise course changes that reflect intelligent navigation, rather than passive dynamics. Yet 3I Atlas follows a smooth hyperbolic trajectory shaped overwhelmingly by solar gravity, with minor modulations that match expectations for outgassing jets. Its path does not display the abrupt shifts or velocity corrections one would expect from an operative spacecraft. If it were under guidance, its behavior would be anomalously clean, not messily comet-like. Communication signatures provide an even stricter criterion. A functioning interstellar probe might emit radio laser or broadband signals for data return navigation or energy transmission. These signals need not be strong, but they would exhibit structure modulation patterns, periodicity, or narrowband frequencies inconsistent with natural astrophysical sources. Decades of CT monitoring have revealed no such emissions associated with 3I Atlas, or with the 7 comets accompanying it. The silence, though not definitive, supports natural origin. An engineered object could in theory operate silently or rely on communication methods beyond current detection capabilities, but scientific inference must rest on what is measured, not on what might be hidden. The swarm hypothesis, suggesting that the 7 comets are themselves artificial probes disguised as natural bodies, falters under similar scrutiny. Each comet has a documented discovery arc extending years or even decades. Their orbits trace back through predictable gravitational histories. Their physical behavior aligns perfectly with well-understood comet dynamics. For them to be artificial would require a deception so perfect that it flawlessly imitates millions of years of orbital evolution. The required level of camouflage would exceed even the most advanced engineering we can plausibly imagine, not because advanced civilizations lack potential, but because such meticulous mimicry provides no strategic advantage. No known technological or strategic rationale explains why an interstellar fleet would go to such elaborate lengths, only to behave indistinguishably from natural comets. Still, the appeal of artificial hypotheses persists. It reflects not ignorance, but a deeper psychological longing, the desire for cosmic companionship, for external narrative, for the reassurance that humanity's story is part of something larger. A universe that includes intelligent visitors feels less indifferent than one governed solely by physics. Even scientifically literate minds find themselves drawn to this idea when faced with unusual coincidences. The timing of Thrace Atlas arriving during a dramatic comet year invites speculation, partly because the symbolism is irresistible. In a world defined by uncertainty, the notion of an intelligible signal can feel comforting. Yet scientific clarity offers its own kind of comfort. The cosmos may be indifferent, but it is legible. It may not communicate intentionally, but it expresses itself through consistent laws. The fact that we can distinguish between engineered and natural origins through spectroscopy, that we can track orbital perturbations with millimeter precision, that we can detect even faint radio signals across astronomical distances. These abilities make us participants in a universe understood not through myth, but through knowledge. And perhaps the alien hypothesis serves a quieter purpose. Even when disproven, it sharpens our awareness of what we do know and what we do not. It forces us to articulate the boundaries of physics, the limits of current detection, the range of plausible explanations. It invites a deeper humility, the recognition that while nature provides adequate explanations for the 2025 swarm, the cosmos remains vast enough to contain surprises beyond our current reach. In this sense, the scientific dismissal of artificial origin is not a rejection of wonder, but a refinement of it. We marvel not because the objects are artificial, but because their natural history is astonishing in its own right. The interstellar visitor is a fragment of another star's story. The 7 comets are relics of epochs long before recorded history. The solar maximum is a reminder that even our familiar sun is capable of behavior both beautiful and disruptive. None of this requires engineering to be profound. The alien hypothesis ultimately collapses under evidence not because aliens are impossible, but because nature in this case is sufficient, and within that sufficiency lies a deeper truth: the universe does not need to be inhabited to inspire us. Its laws are extraordinary enough, its coincidences are compelling enough, its rhythms are meaningful, not because they were designed for us, but because we have learned to read them with clarity, curiosity, and grace. In moments of uncertainty, the human mind gravitates toward the most dramatic conclusions, and nowhere is this more evident than in the rise of modern doomsday interpretations of astronomical events. The 2025 comet swarm, framed by the arrival of an interstellar visitor and amplified by a volatile solar maximum, provides fertile ground for such narratives. Social networks fill with predictions of impending catastrophe, stories of ancient cycles returning, or claims that the sky itself is preparing a reckoning for humanity. Yet beneath these anxieties lies a quieter truth, that our fear of celestial events is woven into the deepest layers of cultural memory, shaped by millennia of uncertainty about the heavens. To understand the modern doomsday impulse, we must first understand its lineage. For most of human history, comets were the heralds of chaos. Their sudden appearance disrupted the predictable night sky, a place otherwise governed by cycles that could be trusted: lunar phases, solstices, the motion of constellations. A comet's unpredictable arrival broke this symmetry and the mind interpreted that disruption as a sign that terrestrial order was breaking as well. During the fall of empires or the spread of pandemics, chroniclers often recorded comets as omens heralding disaster. These associations hardened into tradition, and even in eras of scientific progress they survived as metaphor, superstition, or cultural reflex. In 2025, however, humanity confronts a sky it understands more deeply than ever before. We know the masses of comets, the chemistry of their tails, the gravitational perturbations that send them sunward. We monitor solar storms with satellites, track magnetospheric fluctuations, and model orbital evolutions with high precision. Yet the psychological patterns we inherited do not vanish, simply because we have better data. When several rare events cluster together, comets, brightening auroras, intensifying solar storms erupting, and an interstellar object sweeping past, the instinctive response is not analysis, but apprehension. The mind asks, why now? Why all at once? This layering of events produces what psychologists call apophenia, the tendency to perceive meaningful patterns in random or unrelated phenomena. It is not a flaw, but a survival mechanism, one that once kept early humans alert to subtle environmental cues. In astronomy, apophenia is especially powerful because the sky communicates in grand luminous gestures. A comet tail stretching across the horizon is not easily forgotten. Its emotional impact persists long after the scientific explanation has been understood. The modern doomsday narrative often begins with a misunderstanding of risk. Popular culture has conditioned us to imagine comets as existential threats. Films portray them as planetary bullets, cosmic triggers for extinction. While impacts have shaped Earth's history, the comets of 2025 trace orbits that pose no danger to our world. Their perihelia occur far from Earth's orbital path. Their trajectories, calculated thousands of times over, remain consistent. Even 3I Atlas, fast and exotic as it is, follows a hyperbolic arc that ensures it will exit the solar system long before it could threaten Earth. Yet risk perception rarely conforms to mathematical probability. Humans fear what is dramatic, not what is likely. Solar activity contributes its own distortions to this perception. During solar maximum disruptions to communication systems, satellite operations, and electrical grids can occur with increased frequency. If such disruptions coincide with a bright comet overhead, the temptation to link the two grows strong. A flickering signal becomes ominous when framed by a glowing tail. A regional blackout becomes a celestial omen when occurring during the week of a comet's closest approach. In reality, these disturbances trace back to solar physics, not celestial intention. But the sky's timing feels theatrical, and emotion fills the explanatory gaps faster than science can correct them. The doomsday impulse also reflects a deeper anxiety about human vulnerability. Modern civilization, despite its technology, remains fragile in subtle ways. Power grids can fail, satellites can malfunction, GPS systems can falter. These weaknesses remind us that we are not exempt from the forces of nature, solar storms, geomagnetic disturbances, or atmospheric changes. The fear is not of comets themselves, but of what they symbolize: our dependence on systems we do not fully control, our smallness within the cosmic scale. This vulnerability becomes magnified when the sky grows busy. 7 comets arriving within months, each bright enough to draw public attention, creates a sense of cosmic convergence. Add the rare passage of an interstellar object and the narrative becomes almost irresistible. Humans craft stories not because the universe speaks, but because our minds cannot help but interpret. Science, however, offers a counter-narrative grounded not in dread, but in clarity. It shows that the comet swarm is a statistical anomaly, not a coordinated assault. The orbital histories of the 7 comets reveal no shared point of origin, no synchronized perturbation, no consistent gravitational influence linking their paths. They arrived together not because they were summoned, but because natural distributions sometimes produce clusters. When tens of billions of objects populate the outer solar system, some years will inevitably see multiple arrivals. It is not prophecy, it is probability. Similarly, solar storms peak not because comets are inbound, but because the magnetic cycle of the sun reaches its natural maximum. The overlap between solar turbulence and cometary activity is dramatic but not meaningful. The universe is dynamic enough that coincidences arise naturally. Understanding this does not diminish the emotional power of the moment. If anything, it deepens it. There is something profoundly poetic in realizing that natural processes, uncoordinated, unintentional, governed by physics alone, can nevertheless produce patterns that stir the imagination. The comets are not warnings, but they remind us that we inhabit a system filled with forces greater than ourselves. The solar storms are not signals, but they reveal the living energy of our star. 3s Atlas is not a scout, but it carries the chemistry of a distant world into ours. In this sense, the modern doomsday narrative tells us less about the sky and more about ourselves, our hopes, our fears, our longing for narrative continuity in a universe that owes us none. And perhaps that realization is grounding. The cosmos does not conspire, it simply unfolds, and we fragile observers on a small world make meaning from what we witness. Traveller. As we come to the end of this quiet journey, let your thoughts settle like dust drifting through starlight. The swarm is following 3i Atlas into our solar system not by intention, but through the natural rhythms of the cosmos, and yet watching these 7 ancient comets arrive together still feels extraordinary. They were set on their paths long before humanity existed, while 3i Atlas carries the chemistry of another star glowing briefly in our sky, before continuing its endless drift. Tonight, listener, we explored how coincidence can feel like choreography, how natural patterns can look like messages, and how wonder survives even when explanations are simple. The universe didn't speak, but it didn't need to. Its beauty was enough. So rest now. Let the sky dim behind your eyes. The comets will continue their passage. The universe will keep watch. Stay curious, traveller.